Hello, Juan. How are you?
There it is. Yeah. Hello, how are you?
Great, great. Yeah, it's great to see you.
Yeah, nice to see you.
So let's see, I guess we're still recording. I wonder if I should stop the recording. I guess it doesn't matter. I'm going to introduce you today. I'm very happy to do so. And since both Walter and Karsten have already introduced you, I wanted to ask if I have your permission. Your list of awards is an introduction in itself. Would you mind if I simply pointed out that, you know, these awards, in addition to what Walter and Karsten said, I'll just give these and we'll go from there? Or I also wanted you to know that I wanted to also mention that there have been a number of people that are external to the university that asked if they could join.
Yeah, that's great. Yeah.
And so there is the reflected glory that we get from having you.
Okay.
So that was going to be my introduction. Of course, there's a lot more. There's your work, you know, focusing on the, you know, sort of the quantum gravity string theory, quantum field theory, and relationship between them and all that. I think Walter and Karsten may have touched on that already. But so would you give me your opinion?
On the introduction?
Yes.
Yeah, I think it's fine. Maybe you can shorten the the awards discussion.
I agree. I agree. That will eat up a lot of your time.
Yeah.
Okay.
Yeah, if it's the shorter the better, I think.
Okay, understood. Okay. And so thank you again very much for agreeing to give these lectures. They've been wonderful.
I hope they are going well and they're
Absolutely
at the right pitch. I don't know. It's hard when you cannot see the audience. You don't know what. Usually, when you give a talk and see the faces of people in the audience, you can tell whether they're paying attention or not following or looking confused or interested. Yeah. Here.
Yeah, that's the challenge I have in teaching a course this semester.
Yeah. I guess it must be very difficult. Yeah.
That's right. So.
Yeah, it's hard for the students also. My daughter is in college, so.
Yeah, mine too. So yeah.
Yours too? Okay.
Yeah. So, well, anyway, so I guess what we'll do then is maybe I'll start the introduction at two minutes after 4 or something like that.
Okay, perfect. Yeah.
3 minutes, yeah. And then we'll go from
there. I'm going to close the window. It's a little glare here.
Yeah, I guess I should do the same. I'll return. I'll be right back.
Yeah, sure.
we're going to give it just another maybe minute or two, and then I'll
yeah,
follow through introductions.
Yep.
Okay, then why don't we start? People may continue to join, but I'll start with the introduction. So it's a great pleasure for me to introduce Juan Maldacena. I've heard of you by reputation for quite some time, and I've served on a committee with you once. So this is it's wonderful to do so. So Walter Goldberger began the Leigh Page Prize Lectures by telling about your work, and Carsten Hager, our department chair, also went into some detail about your work and your biography. So I thought, how can I follow that? So I thought I would just rattle off your prizes, and then I'll stop somewhere appropriately in the middle of it, and then we'll ask you to give your talk. So Juan Maldacena has won several awards for his work, and they include, for example, the Galilei Medal in 2019, the Richard E. Prize in Lectureship in Condensed Matter Theory and Related Areas 2018, the Albert Einstein Medal in 2018, the Lorentz Medal in 2018, the Fundamental Physics Prize in 2012, the Pomeranchuk Prize in 2012, the International Center for Theoretical Physics Dirac Prize in Medal 2008, the American Institute of Physics and American Physical Society Danny Heinemann Prize for Mathematical Physics in 2007, the American Physical Society Edward A. Boucher Award 2004. Okay, you get the idea. Or as my wife sometimes tells me, Keith, I'll draw the dots, you connect them. So it's a great pleasure to have you here. And one more thing I'll say, as chair of the committee that serves to get speakers like you here, the number of people from outside of Yale that have emailed us and asked if they could join this, if they could have the Zoom connection information so that they can also join your talk, has been off the scale. So anyway, having said that, Juan will now speak to us today as his final lecture on the entropy of Hawking radiation. So Juan.
Okay, thank you very much for the kind introduction. Let me share the screen and get set up. Can you all see the screen and hear me?
Yes.
Yes, okay. Very good. So, oh, by the way, please ask me questions during the talk. So I welcome questions during the talk. So I will be talking about recent progress on the black hole information paradox. And my talk is largely based on this review that we wrote. And so you can go and find it there if you're interested. And these developments are really based on two papers that did more or less the same thing that appeared in 2019. One was by a then grad student, Jeff Pennington, and then the other by mostly young postdocs. And I'll describe what these papers did in due course. And that this led to an interesting solution, you could say, of one of the versions of the information problem. And there are also other papers by these three authors that solved another aspect of the information problem in recent years. Okay, so the outline of this talk is the following. I will review first the concept of black hole entropy, and then we'll discuss a related concept of the fine-grained gravitational entropy. I'll describe what this is. I'll it will be an important concept in the talk, and we'll see it in quite some detail. And then we'll compute, using these formulas, the entropy of Hawking radiation, so the entropy of the radiation that comes out of the black hole. And the final point is that we will get a result that is consistent with information conservation, as opposed to information loss, which is what Hawking originally had obtained. So we're going to obtain a result different from Hawking's. Now, this talk will not be historical, but hopefully it will be pedagogical. Now, something central for our story is that black holes have a temperature, as was discovered by Hawking. And using Hawking's formula for the temperature, you can understand the first law of thermodynamics. So using the formula for the temperature, you can insert it in the first law of thermodynamics and get the formula for the entropy. And that formula is equal to the area of the black hole divided by L Planck square, or the Newton constant. Here we are setting h bar, c, and the Boltzmann constant to 1 in this formula. And so this is the famous formula originally conjectured by Bekenstein and then made a little more precise by Hawking, by Hawking's result on the black hole temperature. And then another result is that black holes obey a classical area increase theorem. And that theorem, which was understood in classical relativity before these other results were obtained, can now be interpreted as the second law, as a consequence of the second law of thermodynamics that says that the entropy should increase. Now, all the results that we're going to discuss today can be derived using semi-classical gravity. So let me describe what this is. So this is a method for quantizing gravity. And it's a method where we treat the background geometry as classical, and then we describe quantum fields propagating on that classical background, including, for example, perturbative gravitons and so on. And even back reaction due to Hawking radiation is also treated using the semi-classical equations. This approach to gravity makes sense in perturbation theory and has some effective coupling, which is basically the proportional to the Planck length square divided by the size of the black hole, or proportional to 1 over the entropy of the black hole. So the bigger the black hole, the better this type of approaches. Now, there are many features that you don't capture this way, like the detailed energy spacing between microstates that will be non-perturbative, and so those will require non-perturbative accuracy. However, everything we'll discuss today will only require this more approximate theory. Okay, so now we look at the entropy again, and the entropy consists of an area term plus the semi-classical entropy outside. Now, the semi-classical entropy outside is the so-called von Neumann entropy, or quantum entropy of the fields that are outside the black hole. So this diagram here represents a black hole that it represents a star that is collapsing into a black hole. So I will draw in many of these diagrams. So let me briefly explain what these diagrams mean. So we have a black hole geometry, is a 4-dimensional geometry, and we're going to consider spherically symmetric black holes. So we're not going to draw explicitly the directions of the sphere. So on each point on this diagram, we will have a 2-dimensional sphere, and we'll only represent the time and space direction. So the space direction is roughly horizontal, and the time direction is essentially vertical along these diagrams. And furthermore, we're going to rescale the whole space-time so that we can fit it on this page, on the slide. And we do the rescaling in such a way that that light rays propagate at 45-degree angles. So for example, this black line here is the direction of a light ray, or a line along this direction is also a light ray. This region here far away is the region far away in Minkowski space that's been shrunk to finite region here. The vertical line here is r equal to 0, so that's the center of the star. On this line, the 2-dimensional sphere shrinks to 0 size in a smooth way. So this is the center of the star. Here, the red line represents the region where the curvature becomes infinite. So that's the black hole singularity. It's in the future. And this particular light ray that is written here is a light ray that doesn't quite, it starts out from the center of the star and starts going out and doesn't quite make it out of the star. So it goes all the way to infinity, not coming out of the black hole. If you had sent a light ray just an instant earlier, so at this point here, then that light ray would have come out of the star and gone all the way to infinity. If we had sent the light ray a little later, that light ray would have gone on to the black hole singularity. Okay, so that's the meaning of these diagrams. Now, the full formula for the entropy, as we were saying, consists of the area of the black hole horizon. So for example, if we want to calculate, we calculate the entropy on a particular slice of the geometry, so a particular spatial slice that corresponds to calculating it at some time. So we have the area of the black hole at that time, plus the entropy of the fields of all the matter and stuff that is outside the black hole. So that's the total entropy as seen by an observer outside, the total thermodynamic entropy that obeys the second law. And we can calculate it at different times. So here, if we calculate it at this earlier time, this is inside the star. The area is will be slightly smaller, and so on. Now, so these results have inspired the very influential hypothesis, and we can call it like a central dogma in the study of aspects of black hole, quantum aspects of black holes. And it's a central dogma in the sense that it is a hypothesis that is about information similar to the central dogma in biology that tells us how information is processed by black holes. So the idea is that if you have a black hole and you do any experiment you can imagine, but always staying outside the black hole. So experiments you could do are for example, sending a particle into the black hole and seeing what comes out, what type of Hawking radiation comes out. The black hole might evaporate completely. So those types of experiments. So any such experiment can be, the hypothesis is that any such experiment can be described by replacing the black hole by a series of qubits, so it's a finite number of qubits with a number of order the area of the horizon. And those qubits evolve unitarily, so according to a unitary evolution law. So this means that they evolve obeying the laws of quantum mechanics. So that's the hypothesis. The hypothesis doesn't tell us exactly what the Hamiltonian for these qubits is. It only makes the assumption that there is some unitary Hamiltonian, that we can replace the dynamics of gravity, which is somewhat complicated, and particularly the dynamics of full quantum gravity, by this set of qubits evolving with some Hamiltonian. Okay, and so this is a hypothesis. Now, in order to apply it more precisely, we have to replace not only the black hole, but the black hole and some of the region outside the black hole. So some of the region near the horizon. So you put some cutoff here, and you are going to replace everything that lies inside this region, so the whole space-time within this region, by some system of qubits. And the space outside, you can leave it as is, and these qubits then will interact in some way with the space. Are not very manifest in the gravity description. So they are really hypotheses. That's why it's really a hypothesis. It's not something that can be derived by looking at the equations. And some of the results that we'll later see can be viewed as evidence for this hypothesis. But this is a hypothesis that has driven a lot of research in the field, just trying to understand whether it is correct or not. And that's why it's good to spell it out clearly. Now, it's a statement as the black hole as seen from the outside, and the experiments we can do with the black hole from the outside, but no statement has to be made about the inside. Now, there is some evidence about this that comes from more concrete theories of quantum gravity, such as superstring theory, where you can count black holes precisely using strings, D-branes, and so on. There is something that called matrix theory, but I won't discuss that. Gauge gravity duality in string theory also, where you replace a black hole in anti-de Sitter space in a particular negatively curved spacetime by a theory living on the boundary. So there is some evidence for this. However, there is also counter evidence, so counter arguments. So Hawking in 1976 presented an argument saying that this cannot possibly be true. And so we'll go over Hawking's argument now. And the central issue of this argument is looking in more detail at the geometry of an evaporating black hole that was made from collapse. So this diagram represents the spacetime geometry of an evaporating black hole. So it's very similar to the one we drew before. The only difference lies in this little region here, which now here in the far future, this looks like flat space again. So this looks like r equal to 0 in flat space. And this represents the part of the geometry where the black hole has evaporated completely. And so let's start from the past. So the black hole collapses. The star collapses, sorry, the yellow part is the star that collapses into black hole. We form the black hole, and then we start emitting Hawking radiation. So something important is that Hawking radiation is emitted. The process that generates the Hawking radiation generates a pair of entangled particles. One is outside the horizon, and one is inside the horizon. The original pair is in a pure state because they are just coming out of the vacuum, and the vacuum is a pure state. And so if we consider them together, so this Hawking radiation particle together with that one, they are forming a single quantum state. But if we only look at the radiation, they are in a mixed state because we are forgetting about the other one. Now in this way, we are emitting pairs of particles always. And one of the members of the pairs gets all the way to infinity, to the far away region of the black hole. And the other member ends up at the singularity. We don't know exactly what happens at the very end point of the singularity, but at the end point, because that semi-classical gravity approach does not work for that particular point, but at that point, the area of the black hole is very small, so we don't expect that lots of entropy is emitted at during that time. So what we see is that we have an initially, let's say, pure state. We could say the entropy of the star was very small, or we could start with a star that was in a pure state. And then that has gone into a state with large entropy, the entropy of this Hawking radiation. And in this way, with this diagram, what is happening is simply that we are not looking at the partners of Hawking radiation because they end at the singularity. And so from the point of view of the outside, the system looks mixed. So this is somewhat similar to what would happen if we produce an EPR pair, so an entangled pair of particles, and you send one very far away and you don't look at that one, and you are left with only one, then that one you're left with will be in a mixed state. Okay. And here, you cannot look at the other one because it ended up in the black hole singularity. So from this point of view, what the idea is that you can view this singularity region, so the skeptic's point of view, so the people who would say that that central dogma is incorrect, would say that the singularity should be viewed as a sort of new asymptotic region. So they would rethink about this diagram as something roughly like this. You have some initially flat universe where the star collapses. There is some process that is described by the black hole formation and evaporation. And at the very end, we end up with a universe with Hawking radiation and another universe that collapses to some singularity that contains the pairs of Hawking radiation, but we should treat this as a separate universe that could be entangled with the first. And because we forget about this one, nothing that we can do here can measure this one, and therefore we have some entropy. So that was the argument based on the gravitational picture. Now, there is a similar restatement of this argument that goes by the name of the Page curve. So that consists of calculating the entropy of the black hole as a function of time as it comes out of the black hole. So initially, there is no radiation, and then there is more and more radiation, and its entropy monotonically rises as a function of time. So horizontal direction is time, and the vertical direction is the entropy of Hawking radiation. This is just the qualitative form. It's not a straight line and depends on the details, but what's important is that it rises monotonically. On the other hand, the thermodynamic entropy of the black hole, or the area of the black hole, is decreasing monotonically also because the black hole is evaporating. Again, it's not a straight line, but it's some line that decreases monotonically. And it turns out that the contradiction with unitarity, or with that central dogma we were talking about, doesn't occur when the black hole evaporates completely, but it occurs already at the so-called Page time. So Don Page realized that you have a contradiction at this time, and he said that the curve that we should follow is not this Hawking one, but the true entropy of the radiation would at most be the entropy of the remaining black hole. Because the idea is that the origin of the entropy of this radiation is that it's entangled with the qubits. So if that central dogma we were talking about was correct, then when we emit radiation, so the radiation could be in a mixed state if it is entangled with the qubits that were describing the black hole, right? So that is consistent. That's what happens when you burn a piece of paper and so on. But with that setup, the entropy of the radiation the fine-grained entropy of the radiation, I'll discuss. So the true von Neumann entropy of the radiation cannot be larger than the entropy of the qubits, so the total number of qubits that we have, which is equal to the thermodynamic entropy of the black hole. So this is the maximum it could be. So something has to make the entropy of the radiation go down, and it has to go down at least this fast down. Now, there were other apparent paradoxes with the black hole entropy formula, and we discussed a bit already some of them last time, so I won't dwell on them very much. So the Schwarzschild solution had two sides, two asymptotic regions. There is, yeah, maybe I won't discuss this one in great detail. And we will see how to resolve these confusions. Now, these confusions involve mostly the black hole interior. And we discussed last time that when we have two entangled black holes, when we have a geometry connecting the black hole interiors, we should think of them as entangled states of those qubits that appear in the central hypothesis or central dogma. Now, the rest of the paradoxes involve an understanding of the fine-grained entropy. Now, there are two notions of entropy, and it's important to keep these two notions apart for this discussion. First is the so-called fine-grained entropy, or sometimes called von Neumann entropy or quantum entropy, or in some contexts, sometimes it's called entanglement entropy. So this entropy is defined as follows. So if you have a quantum system described by a density matrix rho, then the entropy is a trace of log rho. So this is similar to the Shannon entropy, except for quantum systems. And it's the true entropy of the system if we are able to do arbitrary measurements on the system, arbitrary complex measurements of the system. This is the actual entropy. Then there is the entropy we ordinarily use in thermodynamics, which is we can call the coarse-grained entropy. And this arises from the fact that we are only not measuring everything we could possibly measuring, but we measure sort of simple observables. So if we only restrict to measuring simple observables, we can have some thermodynamic, we can calculate the entropy of the system that way. And it can be bigger. So it has a precise definition in terms of the von Neumann entropy of the density matrix with the maximal von Neumann entropy that agrees with the original density matrix on if we observe them with simple observables A. Simple observables could be the energy, charges, densities, etc., energy densities, etc. But this is the usual thermodynamic notion of entropy, which obeys the second law for an isolated system. So if we start, for example, just to distinguish the two notions of entropy, let me give an example. Suppose you have a room where all the gas in the room is put in a little bottle, right? So that little bottle has some initial entropy. And now at time equal to 0, you open the bottle, and then the gas will spread throughout the big container. And in this process is a unitary process where described by the unitary evolution of quantum mechanics. In that process, the von Neumann entropy would not change. It will be equal to the initial entropy. However, from the thermodynamic point of view, the gas now occupies a bigger volume and will have a bigger entropy. So the entropy that we talk about in the second law has increased through this process. It's an irreversible process that has increased the entropy. Okay, so the difference between the two is that when we look at the gas now occupying the room, if it was produced by a state that at equal to 0 was in the bottle, it's not the most generic state. It's just some subset of the possible states that would contribute to the full thermal ensemble of the gas in the room. Okay, but that difference is hard to tell at late times, so after t equal to 0. And for that reason, when we talk about the thermodynamic entropy, we ignore that difference. Now, for the moment, we'll be talking about the black hole as seen from the outside. So when we talk about the entropy of the black hole, we can think that we are talking about the entropy of the quantum system that was appearing in that central dogma. So if we replace a black hole by a piece of coal, that's roughly the entropy we're talking about. Now, the important point is that the area of the horizon, the entropy defined as the area of the horizon, should be viewed as a thermodynamic entropy, because when the black hole, for example, forms initially, you go from a state with where the area of the horizon is very small at equal to 0 to something that is increasing. Now, the question is whether we can compute the fine-grained one. Now, for generic systems, it's very difficult to compute the fine-grained entropy. But for systems that are, for these gravitational systems, it turns out that there is a formula for the fine-grained entropy. And the formula, well, had a long history and only some pieces were discovered first and so on, but the final formula is as follows. So it's also involves some area. So it's similar to the formula we had before. It involves an area and some entropy outside. So there is a point here. I will explain what this point is. This point is a two-dimensional surface. In these diagrams, we are not drawing the two-dimensional surface of the sphere around the black hole. And then it involves that point, the area of this point, and then the entropy of some region that joins this point with this so-called cutoff surface, which is where which we are using to define the entropy. Now, the idea is that you compute this quantity, and then you vary this point in your space-time, so you move it up and down and so on, so as to extremize. First, you find an extremum of this quantity, so you find a point such that when you vary it in any direction, the first derivative is 0. And if there is more than one extremum, then you minimize over all possible extrema. So that's what you're supposed to do. This is a surprising formula, because for ordinary systems, we don't have a simple formula for the fine-grained entropy. This is something special about black holes. Now, let me give you some examples to see how this formula works. So imagine you compute the fine-grained entropy at some time just after, let's say, a black hole has formed. So this is the diagram of the evaporating black hole. So the star forms, and just after it has formed, you calculate the fine-grained entropy. Now, the idea is that the formation of the black hole is a unitary process, so the fine-grained entropy should not grow too much. And indeed, the one that extremizes, the point that extremizes the entropy is actually at the center of the star, and will have 0 area. So the area piece doesn't contribute, and there is a volume term here, proportional to the entropy along this slice, and the entropy will come mainly from the entropy of the star. So we get the result, which says that the fine-grained entropy after the black hole forms is actually equal to the entropy of the star, which is the same as the entropy it had before it formed. So that's a very pleasing result, because it's showing that we get the result consistent with the interpretation of this quantity as a fine-grained entropy. Now, the main result in a couple of years ago by these authors whose pictures we saw in the beginning is that there is a second extremal surface. So there's a second surface that extremizes that quantity that we discussed that arises sometime after the black hole starts evaporating. So there's a precise notion of how long it is. So it's not too long afterwards. So it's a term proportional. Rs is the light crossing time of the black hole times the logarithm of the entropy. Logarithm is a slowly varying function. So this is not a very long time. After that, you find a new extremal surface, which is somewhat close to the horizon. I won't discuss exactly how to find it, but the important point is that the presence of Hawking radiation is important for solving the minimization equation we discussed. And the other important point is that its location is close to the horizon. So the area of the surface is close to the area of the horizon. And so now we have two extremal surfaces. So one is the one, so at any time during the black hole evaporation, we have one extremal surface which corresponds to the zero area one, so that we have, so this has zero area, it obeys the extremality condition, and the entropy is actually equal to the entropy of everything that lies on these slices. So initially the entropy is very small, the entropy of the star, and as the black hole evaporates, the entropy becomes larger and larger because we accumulate the entropy of all the partners of Hawking radiation. So we start having an entropy that rises and is similar, and in fact is actually equal for this case to the entropy of the Hawking radiation, because the entropy of the Hawking radiation comes out from the partners here, which are entangled with the ones here, and together they are in a pure state, so the entropy outside is equal to the entropy along these surfaces. So that's what we have for the black hole from one of the surfaces. And from this new surface that these authors found, we find an entropy which is proportional to the area of the horizon. So it's a decreasing entropy, and it follows the area of the horizon. And we are supposed to take the minimal of these two. And so we choose the minimum one, and then we have a formula for the entropy of the black hole that follows a curve which is similar to the Page curve. Now, the Page curve was, so it follows a curve similar to the Page curve for the black hole, but what we really wanted was the Page curve for the radiation. So we wanted to understand how to compute the entropy of the radiation. Now, the radiation lives far away in a region where quantum gravity effects could be very small. I mean, if we were in anti-de Sitter space, it could have left anti-de Sitter space, or if not, it could be collected into a quantum computer that is far away. And so that's where there is some quantum system where the radiation is encoded. And since we obtained the state using gravity, well, however, there is a little, so naively, given this first point, we would think that it's straightforward to calculate the entropy of the radiation. We just have to do the same calculation that Hawking did. However, there is a little glitch, which is the fact that since we obtained the state using gravity, so we obtained the state using gravity, we should still apply the gravitational fine-grained entropy formula for computing the entropy of such a state. And so when we apply this formula, what do we do? So we are interested in calculating the entropy of the radiation that lives here outside. But the fine-grained entropy formula tells us that we should add little areas and regions and maximize over all possible regions. And in this case, what we can do is we can include a region here, which goes from the interior to this surface, arbitrary point here. And by including this region, it might be convenient sometimes to include this region because of the following thing. So by including this region, we can lower the entropy because we would be catching the members of Hawking radiation here, and then we would be catching also the partners of Hawking radiation in this region, and together they form a pure state. So those members which have those pairs that have one member here and one member here will not contribute to the full entropy of the system. And so in this way, we can lower the entropy. By including this area, we pay a price. So this is like something big. So we pay a price due to the fact that there is a non-zero area here, but we gain something from the fact that this entropy can be smaller than the entropy of purely the radiation itself. And so by including these two terms, it might be convenient to select to have here a non-trivial point. And in fact, when you actually do the calculation, you find that indeed you find an extremal surface here, so some point which obeys the extremality condition that we were discussing for the fine-grained entropy. And in fact, it's the same surface that that Pennington and company had discussed. So in fact, if the initial state is pure, so yeah, as we were discussing, then the two quantum extremal surfaces are the same as the ones we discussed before, and we get the Page curve for radiation as we were expecting. Now, the skeptic would say, well, this is just an accounting trick. The skeptic would say, I have always said, if you include the black hole interior, then the state is pure. So the information problem arises because you don't have access to the interior. This is what they would say. But it's not really a trick that one has invented. It should be viewed more like an oracle. This trick can be derived from the gravitational path integral by deriving that fine-grained entropy formula that we discussed. Maybe I'll explain a little bit how this is done. And so it follows from the rules of gravity. And in some sense, it is an oracle in the sense that it gives us the true fine-grained entropy of the exact state, but only using the semi-classical state. I emphasized in the beginning that these computations are done just using gravity as an effective field theory. We don't need any fancy theory of quantum gravity, such as string theory and so on. All the formulas we're discussing here can be computed in ordinary gravity theories. We can compute them for general relativity and evaporating black hole in general relativity, etc. But it will give us the true fine-grained entropy formula for the exact state, an approximation to that, but a good approximation to that fine-grained entropy formula. So now I will say a few words about deriving this, the fine-grained entropy formula. And it's conceptually similar to the derivation of the black hole entropy using the Euclidean black hole. Let me see, how am I doing with time? When you consider a Euclidean black hole, you take the black hole metric and continue time to Euclidean time, and then you notice something interesting. So you find that if you make the Euclidean time a circle, then the point that was the horizon looks now like a smooth surface. So by choosing this period of the Euclidean circle appropriately, by first making the Euclidean time into a circle, and then choosing its period appropriately, we can have a completely smooth Euclidean solution where the horizon is a completely smooth point. Okay. Recall that in Lorentzian space, the horizon is always a smooth point. In Euclidean space, if we either not make this a circle, or we don't make it with the right value, then we would have some singularity here. But by taking it to be of the right size, we have. Now, what is this size of the circle that makes it smooth? Well, the size of the circle ends up being just the same as the inverse of Hawking's temperature. And so we can think of this geometry as describing a black hole in thermal equilibrium with a bath. So this size of the circle here establishes the inverse temperature of the bath. So when we consider a Euclidean field theory with a circle of finite size, that's equivalent to considering a field theory at finite temperature. And so then we can consider the whole thing as being thermal equilibrium, a black hole in thermal equilibrium. And then we can compute the gravitational action. So we can compute the gravitational action on this background. And we can interpret this gravitational action as giving us the trace of e to the minus beta h, where h is that mysterious Hamiltonian that acts on the black hole microstates. So what we can really calculate is here the gravitational action using semi-classical methods. And we reinterpret that using that central dogma we discussed as this quantity.
Juan, may I interrupt with a question?
Yeah, please.
So I'm wondering why or what approximation is being made in using this sort of thermodynamic equilibrium formalism
Yeah.
describe a black hole that's evaporating.
Yeah.
Maybe I missed something, but
yeah,
so
yeah. So right now we're describing.
Yes.
Yes, very good. Good question. Yes. So right now we are describing a black hole in thermal equilibrium. So we're not describing an evaporating black hole.
Okay.
So this, what we see here is a black hole in thermal equilibrium. So if we continue this to Lorentzian signature, it would be a situation where we have a black hole and we have thermal radiation coming into the black hole at the same rate that is going out of the black hole. Yes. And the black hole mass is not changing. That's what this geometry is describing in Lorentzian signature, in Euclidean signature. Well, it's just this geometry. But using this, we can calculate the entropy by taking the derivative with respect to the size of the circle. So we pick the size of the circle, we find the black hole with appropriate mass so that there is no singularity here, and then we vary the size of the circle, and we get some number, which is the entropy, and it, well, of course, gives us the area formula. This is an alternative way to derive the area formula for the entropy. But something important in this way of thinking about it is that you fix the size of the circle far away, and then gravity chooses the geometry here dynamically so that it is smooth. And in this way, we are computing by computing the action, we compute the free energy as a function of the temperature. Now, we can think of this gravitational path integral equivalently. We can imagine that we open up somehow this circle, and we think of this as a way of computing a density matrix. So if we were to be able to include a complete set of states here, we would be able to compute, think about this as a density matrix. And if we, then we could compute the entropy by taking the trace of that density matrix to the nth power. And if we can, then that would correspond to a calculation where we go around the circle n times and then we connect them again. So in that calculation, there's only closed circles. And we don't have to discuss how to introduce a complete set of microstates. So here, the name of the game is that you never talk about explicitly about the whole set of states that describes the quantum gravity Hilbert space. You only talk about complete traces over that set of microstates. Notice that, yeah, maybe I should have emphasized that when we talk about the Euclidean black hole. Sorry, I'm going back to the previous transparency now. I realize I should have emphasized something. What we can compute is this gravitational action. The idea that there is a set of microstates and we're computing this trace, that's a hypothesis. And we're trying to test this hypothesis, but we don't, in principle, know whether this hypothesis is correct or not, just from these gravitational formulas, okay? In particular, we don't have an explicit description of these microstates. So things that we can do is take the trace of rho to the n, for example, by doing a path integral where we go around n times and we have a closed circle, then that can be done. And if we can do that, then we can do it. So we can do it not only for a circle, but for something which is not exactly a circle. So we make a small deformation of the circle here. The small deformation means, for example, sending a gravitational wave, right? So we make deformation of the space-time geometry, and we send the gravitational wave. In this way, we can prepare a new density matrix, which is not exactly thermal. And this one, we can, again, raise it to the nth power, so for example, to the cubed power. And when we raise it to the cubed power, the cube power, the third power, so then we get a geometry which at the boundary will contain 3 of these deformations. And then we have to find the smooth geometry in the interior that describes that. And if we can calculate this and then analytically continue in this power, so go from 3, 4, 5, etc., it turns out that it is possible to do this analytic continuation without finding all the solutions. And you can argue that after doing this analytic continuation, the formula that you find for the entropy is actually equal to the area to that formula we discussed before as simply a conjecture. So that formula can be derived from the gravitational path integral. That's the point. So if these arguments were not clear, let me just say that the summary is that we can start using the formulas for path integrals, for gravitational path integrals, and derive this entropy formula, okay, in a way that is very similar to this this Gibbons-Hawking derivation of the black hole entropy formula. Now it turns out that if you have a state that is prepared by a Euclidean path integral, and it has gravitational dynamics only in some regions, then we should allow various topologies in that region. So for example, if you are computing the entropy of Hawking radiation, and you prepare that state by collapsing a black hole, and all that can be described by the gravitational path integral, then you can calculate the entropy of the radiation, and it will involve a series of geometry similar to what we discussed, but we are allowed to connect the interiors of those black holes in an arbitrary way, because in gravity we are allowed to consider different topologies, and if you connect the interiors of the different replicas that appear in this formula, so here I should have mentioned that when we compute rho cubed, we have three of these gravitational waves we are sending, so we have like these are called three replicas, and the geometry could connect these various replicas. And so there are some geometries I won't, perhaps don't have enough time to describe all the details, but the central idea is that there is some region outside where we're computing the entropy. That's this region here. But then the black hole region interior can be either connected within each replica or among the different replicas. And these different topologies can give us the right answer when we calculate the entropy at late times. They reproduce the formula that we said before. And in the end, we get this formula, the formula of this kind. Now, so far we only talked about entropy, and but these formulas about entropy are telling us something about the interior. And so far we discussed this central dogma hypothesis as talking about degrees of freedom that describe the black hole from the outside. But you can ask, what part of the interior do these degrees of freedom describe? Do they describe all of the interior, none of the interior, or part of the interior? And if so, which part? And it turns out that the right answer will be that they describe some part of the interior. But to explain which part, we'll introduce a concept which is basically telling us which part it is. And it's the concept of entanglement wedge. It's saying that it's the causal domain of dependence of the region that appears in the computation of the entropy. Let me just explain with a picture of what that means. So it's better to explain that with an example. So imagine that we are computing in green so we have some time here. We have a collapsing black hole, and we compute the entropy at time t. That involves a minimal surface that went all the way to the center of the black hole, right? This was the correct answer for early times. And then we look at all the space-time points whose state we can predict from initial data on this surface. So that will describe a portion of space-time that has the form of a wedge. So that's why it's called the entanglement wedge. But the name doesn't matter too much. But so there will be this whole region associated to the computation of the entropy. So the entropy involved the state of quantum fields along this slice. And if we know the states of quantum fields on this slice, we can determine everything in this whole space-time region. Now, at late times, we saw that there was an extremal surface that was near the horizon. And so if we compute at late times, the region where we compute the entropy is a space-like region going from here to here. And the only portion of the space-time we can determine from there is this green region that we see here. Okay, So that's so the idea is then that the black hole degrees of freedom describe at early times they describe this whole green region. Okay, so they describe the black hole from the outside, and in addition they describe this whole portion of the interior. Okay, not the white portion, just the green portion. So this green part, and on the other hand, at late times, they only describe this little green portion. So in particular, they don't describe anything, not the white region and not the blue region, only the green region. Okay. So a smaller portion, and so on. Now, if we compute the look at the radiation, so if we look at the, if we imagine we are collecting the radiation here, and we can do arbitrarily complex operations on the radiation, then the idea is that we can only describe the physics of what's happening in this region. However, at late times, we are computing the entropy of the radiation in this region. However, there is this portion of the black hole interior that is also contributing to the computation of the entropy of the radiation. It was this portion was important because it was lower in the entropy of the radiation. And the idea here is now that the information of what's going on in this region can be recovered from arbitrarily complex operations that we do in the radiation. So if we do simple operations in the radiation, we can only see what's going on in here. But if we do very complex operations in the radiation, we can recover what's going on in this region. And when the black hole has evaporated completely, then by doing arbitrarily complex operations on the radiation, we can recover everything that goes on in the black hole, everything that goes on in the interior of the black hole. I should mention that this statement about what portions of the interior we can describe from which regions is partly conjecture, but there is more and more evidence that this conjecture is reasonable. So in other words, the quantum system that describes the black hole from the outside also describes everything that is included in its entanglement wedge, right? And there is a precise meaning of what that means that I will not discuss. Okay. I think I'm. Now, there was a paradox that was discussed in recent years. It's called the AMPS paradox, or sometimes called the firewall paradox. It's just a version of the black hole information paradox. And these authors, Almeri, Maroff, Polchinski, and Sully, they derive this paradox by assuming these ideas of the central dogma that I mentioned, plus one further implicit hypothesis that the interior operators act on the Hilbert space of the black hole, the same Hilbert space that appears in that central dogma. And the resolution of this is just simply that that's not true. So, well, I have here a more detailed analysis of that, but maybe I'll ignore this. So in conclusions, we reviewed the gravitational fine-grained entropy formula, and we applied it to the computation of the entropy of the radiation and obtained results that are consistent with unitarity. And at late times, most of the interior is part of the radiation and not part of the black hole degrees of freedom. So the degrees of freedom that describe the black hole as seen from the outside. Now, you can ask, what was Hawking's mistake? Well, it was simply not to use this fine-grained entropy formula. Of course, he didn't know about the fine-grained entropy formula, but that's the only difference between what Hawking did and what we are discussing today. Now, I should mention that a lot of what we discussed was initially derived by thinking about aspects of the so-called ADS-CFT correspondence, which itself involves some string theory. But for the purposes of this talk, you only need gravity as an effective field theory. So if you want to apply these formulas, you don't need to know anything about ADS-CFT or string theory. You only need to know gravity as an effective field theory. So the simplest quantization of gravity. And I have to say that there is an amazingly deep connection between gravity and quantum mechanics. That these notions of fine-grained entropy, which are detailed quantum properties, are encoded by geometric properties of the black hole. Now you can ask whether the information puzzle is solved. And we could say that one aspect of it is solved. So the aspect that involves computing the entropy of Hawking radiation, that is solved, and is solved in the sense that we now get the right entropy directly from the rules of gravity without having to make any assumption. But there is another aspect that is not understood, which is to describe what the state of that Hawking radiation is. So if we want to describe exactly what the state is, then we don't know how to do it yet. So these replica wormholes we discussed to compute the entropy, that they compute the entropy, but they don't tell us what the exact state is. And in some ways, these entropy computations are similar to the entropy computations of black holes, which tell us the total entropy, but they don't tell us the microstates. Now, if you assume more like string theory and so on, or ADS-CFT, then you get some picture for those microstates. But the goal here is to explain those features directly from the theory of gravity. And okay, I think I'll finish here. I was going to mention. I was just mention what we expect for the future. So we would like to understand what further lessons this is teaching us about the black hole interior. In particular, what is the proper interpretation of singularity? So that's something that hasn't been understood yet. And the biggest goal of this whole question about black holes and so on is really to find some interesting implications for cosmology, because it's likely that an understanding of, for example, the black hole singularity will teach us something about the cosmological singularity at the beginning of the universe. And that's really the ultimate goal of research in quantum gravity. But so far, we've been thinking about problems involving black holes. Okay, thank you.
Okay, great. Thank you very much, Juan. And we have time for a few questions if you have any. I don't know if raising your hands electronically will work. We could give that a try. Otherwise, it'll become a free-for-all. But if you want to ask a question now, I'll skim through and see if anyone has a raised hand. So Steve Gervin and then John Harris.
Thanks, Juan. Very interesting. Let me just ask an incredibly naive question to see if I have some of the idea about the microscopic versus microscopic. So
yeah, please.
In the original Hawking picture, there's a kind there's no back action on the geometry from the microscopic emission events. And is that, when you take that into account, does that produce correlations in the?
No.
That's not it. Okay.
No, that's not it. And even Hawking discussed that why that is not enough. So there was this diagram of the evaporating black hole that we showed that diagram takes into account the effects of back reaction.
I see.
So just simply the fact that the mass of the black hole decreases. So
well, but that's only a sort of mean field response, right? That's not, there's shot noise. There's individual particle emissions.
Yeah, you could take that into account, but that's believed not to change the answer.
I see. Okay. Yeah. Thanks.
Sure.
Okay, John.
Yeah, Juan, thanks for these 3 great lectures. Let's see, I have a simple kind of general question and then a more specific one. The simple one is the takeaway from what you said in this lecture, that you can explain the entropy simply from gravity, but you actually need quantum gravity to understand the state?
Yes.
Okay. And then the other question, great, thanks. I understood that part. If you go back to your first space-time diagram where you had Hawking radiation, can you go back and we can take a
Yeah.
look at it? I have a question.
I like to answer the previous question a little better.
Yeah,
So,
please.
So for calculating the entropy is enough to use semi-classical quantum gravity. So the quantum gravity treated in a simple way, right? Just gravity. And to compute the entropy, it's enough to take the original background and look for these minimal surfaces and so on. But presumably to compute the state, we need some better theory of quantum gravity than just the semi-classical theory.
Sure.
That's the idea.
That I can understand. Okay.
But now, yeah, I can go back to your second part of your question. Let me.
It had three kind of green curves. You had the star evolving in time. It was one of the first diagrams you had.
The beginning. Okay.
It was a second one that you had, but okay.
This one?
No, farther. You had Hawking radiation by then.
This one.
Yeah, that one. So my question was, given what you said about the entropy, can you go back? Somehow I missed the part where you explained the three different green curves.
Ah, good. Yeah. So these green curves are different spatial slices at different moments in time. So this is so in these diagrams, time goes in the vertical direction.
Right.
And so when the green curve can be viewed as the set of points in space at a given moment in time. So after choosing some suitable time coordinate, there are many different ways of drawing these slices, but this is just some particular choice of spatial slices. So here we can say, well, we have the exterior and then a portion of the interior, right? So here we have a bigger portion, and here we have an even bigger portion of the interior, and have some exterior geometry.
So that part I didn't understand, the C. So it's a late time, and you have a large portion of the interior, and
yeah, so this is trying to, so these curves are trying to represent that at this time you don't see Hawking radiation either in the inside, either the partner or some portion outside. Okay. On this slice, you see, for example, this red mode, but the blue mode hasn't been created yet.
Okay, right. Okay,
now you see the red mode here outside and the red mode inside on this slice. Now, if you choose this slice at late times, then you see more. So you see the red, the green, the blue. So all these other modes we would see.
Okay, so it's late time and the radiation escapes, and then you have the part. Okay, that explains it. Thanks so much.
Right. And then there is this one at the very late times where it's only outside and captures all of the Hawking radiation.
Right, and then, okay, so there's no entangled partner there?
Yeah, so the entangled partners are, so on this slice, they are inside, but they are not part of this slice D somehow.
Okay.
Yeah, you have the option of including or not including the interior, but you don't have to. So here, on these slices, the space doesn't end until you get here. So you have to include both of them. But here, this is a complete slice outside that does not.
Okay, so you're way past the page time or so, and then therefore.
Yeah, the page time is somewhere here, right? Yeah. This time is when the black hole evaporated completely. And here it has completely evaporated, and we only see the radiation.
Okay, perfect. Thanks.
Sure.
Okay, so I don't see any hands raised now. I guess we've gotten everybody. Have I missed anyone? Okay, so then let me just end by thanking you, Juan, for a wonderful set of Leigh Page lectures. This is wonderful, and you were in the company of some great people in giving the Leigh Page Prize, and this has just been outstanding. So thank you so much.
Okay, thank you very much for the invitation, and best wishes for everyone.
Same to you. Thank you.
Hope to see you in person soon.
Exactly. I hope so.
Yeah.
Okay. Okay. Bye-bye.
Thanks, Juan.
Sure. See you.
Bye.
Hey, Keith.
Hey, Walter. So,
We should probably send him an email thanking him.
okay, all right.
I can put something together and we can.
Okay, wonderful. Thank you. Yeah, I really would appreciate that. This was wonderful. I mean, he really took the time to
He really did take the time.
yeah, to put it all into this Leigh Page lecture. So yeah, would you then? And thanks very much. Thank you for inviting him, Walter. This was great, man. Do you realize the number of people that have asked, even from other countries, can they?
Right. Yeah.
Yeah.
That's good. I'm glad. We also have it, I imagine, I guess we record these and post them online, I assume. Right?
They are recorded. I'll ask Terry, are they online? Can we somehow retrieve them?
I think it'd be worth it.
Yeah, exactly. So I'll ask her and I'll.
We probably should ask him if Juan, if it's okay with him, but
she's already asked him if he's
she already
okay
did
with the recording. I don't know about posting it online, but
that's what I mean, posting it on the web.
Okay, all right.
Yeah, I'll put it in the. I'll write this. I'll compose an email and I'll send it to you tonight or something.
Okay, fantastic.
Yeah.
Okay, great. Thanks.
Yep.
All right, and again, Walter, man, this is wonderful. I'm glad you got in here. So thanks.
Right. I'll see you around.
Okay, man. All right. Take care, everyone.